Okay, consume Batman music. My phone ran out of battery, so if you want to hear the music, which of course you do, you're going to have to watch The Dark Knight or The Dark Knight Rises, or back to back, because I know it's hard to choose. But although Dark Knight is better, but I do really like Bane. So this video is about the approximation of a binomial distribution using the normal distribution. Now, to be honest, on the surface, this actually is quite pointless because your calculators are so good that if you have x is modeled as a binomial, right, you can, in your calculator, I've tried it, try putting in like a million values, I don't know, with say probability of success is 0.2, and your calculator can do it. It used to be that we used to use tables and n. Remember, this is your n and this is your p. N only went up to 50, so we would have to switch and convert and stuff like that. But there is still a purpose to it because your calculators will crash if you have n being an absolutely massive number. It wouldn't be able to put in like a Googleplex or something, for instance. We would have to convert to a normal distribution. All right, so it's not a completely pointless exercise, and in a way it's really good because you can use your calculator to check your answer. Okay, so when can we convert a binomial to a normal distribution? Well, the answer is we can see quite quickly using autograph what happens. So if for starters I pick a binomial distribution with with n being 10 and probability of success being 0.5, I can see this here is the probability density, right? So I've kind of mapped out what the probabilities are for each number. You can see that this is pretty symmetrical, isn't it? It kind of looks like a bell curve. But actually, the error would be quite big. It looks like a bell curve, but because there are so few numbers, and therefore the relative gap between the numbers, which we'll talk about in a bit, is quite high, actually the error would be quite big. But you can see that when p is 0.5, it looks really symmetrical. And if I change that to say 0.1, it doesn't look symmetrical at all. Actually, what I've got is I've got this slope, because remember it starts from 0. I've got this slope like this. It's very skewed. It's not symmetrical down the middle at all. Okay? And I'm going through this quite quickly because I don't know how much detail you really need because you're doing mechanics and stats. It's a different scenario to the old A level. Right. So what was if n was 100? Well, you can see that this looks very good. We've still got our normal distribution kind of curve shape. So like here, that looks quite good. And p here is 0.5, so it's looking very symmetrical. And it looks nice, but again, the relative gap between each number is still kind of big, really, in the grand scheme of things. But our error wouldn't be too high. Now, again, if I make p being 0.1, you can see that it doesn't look symmetrical at all, really. I mean, you can see it's still skewed towards that left-hand side. Well, actually, it's more towards the right. This side is bigger than this side. It's not symmetrical. All right? And then if I go to, this is 1,000, actually. Okay? So, whoops. This is n being 1,000. And n and p is 0.5. Now the relative gap between them is quite small, and you can see we've got really good symmetry, and that the numbers look really close together, like I've already said. And again, if I made my p being small again, so this is actually 0.1, sorry. If I make my p being 0.5, where's that gone? Cool. So when p is 0.5, it's looking really symmetrical. Obviously, it looks almost perfect. And then when p is 0.1, you can see that you can see what we had before. It looks almost completely symmetrical. which is why it's reasonable for me to mistake it at first. I mean, it's not quite actually, if you look at it, it's not quite symmetrical, but the point is that when n was 10, the lack of symmetry was really obvious, wasn't it? When n was 100, it's still kind of obvious, but now when n is 1,000, it's not very obvious about the lack of symmetry. So we need symmetrical, as symmetrical as possible, a distribution for it to be modeled to a symmetrical distribution, which is the normal distribution. All right, so what we're saying is that n needs to be large in order for this to work, and that p needs to be close to, so p needs to be approximately 0.5 to keep the symmetry. So the larger n is, the less close p needs to be to 0.5, because it kind of mitigates that error. The margin, the error between approximations lowers as n increases in size. But it still doesn't really make sense to approximate a binomial to a normal if your p is like 0.01. I mean, that's not symmetrical at all. So what we used to say is a good kind of a good reason to approximate it was that NP, so n times p is greater than 50. Okay, and that's something you should bear in mind for when you're doing your exams and it's asking you questions about it. But that probably is because of the historic tables issue. So that's that. What does it even look like, a distribution? So if you've got a binomial NP, okay, remember n is number of trials, p is chance of success, then what this turns into is a normal distribution which you know is the mean and the standard deviation squared. The mean of a binomial distribution is n times p, which can be proved, but we're not going to do it here because it's just really quite in depth. So let's say we had something like x is b and we've got 100 and it's 0.2, let's say, which again isn't a great distribution because np is not above 50 here, right? But we'll do it anyway. So np, 100 times 0.2 is our 20, okay? So the mean is np, and the standard deviation is the square root of npq, where q is 1 take p, okay? So in this case, p is 0.2, which means q would be 0.8 because it's 1 minus that. So npq, 100 times 0.2 times 0.8, all square rooted is 4, and we'd put the squared in there just to make sure we've got that variance. So we always understand that 4 is the standard deviation and 20 would be the mean. That's how we would do it, okay? But we need to bear this point in mind, that binomial, and that's why I was talking about gaps between numbers relative to the number of numbers we're talking about. Binomial distributions work with discrete data. Normals work with continuous data, right? So we're going from a lollipop kind of system to a continuous curve. So that means this gap between numbers needs to be accounted for, because you know that probability is determined in a normal by finding the area beneath the curve, right? But if I want to know the probability of, say, x equaling 20, in a normal distribution, this would be 0, because 20 is just a line, and the area of a line and a line has no width. The area of a line is 0. So what we need to do is we need to take the upper and lower bound of the number 20, so 19.5 and 20.5. And so if I wanted to know the probability of it equaling 20, I would have to take the area between the upper and lower bound. Do you see that the number 20, when it comes to the normal distribution, isn't really 20? It's either 20.5 or 19.5. It's that space in between, because that has, however slim, an area. Okay, I hope you understand that. And this is called the continuity correction, and that's something we need to work with in order to even find results, okay? So let's say x is binomial. Let's do some examples. X is binomially modeled this way. So we would approximate this if we were being asked to. Again, we don't have to, but the question will say do it. So we'll say that's y, n, and we know that the mean and the standard deviation squared, so the mean is np, and the standard deviation is npq. So therefore, NPQ square rooted, so therefore the variance is that whole thing squared. So NP 150 times 0.45 is 67.5, that's our mean. Times that by 0.55, because remember Q is 1 minus P, and square root that. So we get 6.093 all squared. Okay? So, so if we go to our calculator then, if I want to find the probability of x being greater than 60, this is approximately, because remember it is approximation, the same as probability of y is bigger than what is 60. Remember we just talked about this. If we have our standard deviation, remember our, not standard deviation, our normal distribution, we know the mean is in the middle, 67.5. We're trying to find bigger than 60, but that area of 60 is 0, okay? And what is 60? We said that 60 is its upper and lower bounds, so 59.5 and 60.5. So if I want to find bigger than 60, remember 60, it's this whole section here. So what's bigger than 60 is everything larger than 60.5. Okay, so everything larger than 60.5 because, and sometimes I like to do this, like this is 60, 59 point, so if I was doing a practical question, this is how I would lay it out. 60.5, it's not inclusive, it doesn't include the whole number, so therefore it's everything beyond 60.5, okay? And we can see from the diagram that that's the same as 1 minus the probability of y less than 60.5 because that's how our calculators work, yeah? So this is the same as one take, and then we can go to our normal calculator stuff. So we've got 7, we got a normal CD, we go minus 1,000 like normal, and then we go 60.5, we got our standard deviation 0.093, and we got 67.5 as our mean. So that's that. So 0.125306, blah, blah, blah. We'll do store A like we normally do, and then we'll go down and we go 1 minus our alpha A, and we get 0.874, well, 5 to 3 sig fig, right? Now, because I'm curious, and I'm sure you are too, by chomping at the bit, wanting to know, well, how far out is that? So, because our calculators can actually do the binomial, why don't we check? So, if we're going back to our x is binomially 150, 0.45, if I want to find the probability of x greater than 60, that is the same as 1 minus the probability of x less than or equal to 60, if you remember, right? Because we're dealing in whole numbers now, okay? So 1 minus, let's go to our binomial distribution. So that's 7. We go down, binomial CD. We got variable. Whoops, I pressed the wrong thing again. 7, down, 1, variable. Okay, cool. So 60. N was 150. P is 0.45. How far out are we going to be? So this is 1 minus 0.12508, blah, blah, blah. We'll do that store A again, store A. We go back to our thing, and we go 1 minus alpha A, and we get 0.8749. So what, 0.875? Wow, really close, really close. That's awesome. I wasn't even expecting that. I wasn't even expecting it to be that close. I mean, you can see it's still a bit crap, but either side, it rounds to the same number, to 3SF. Awesome. So, mystery solved. Is it a good approximation? Yeah, that's all right. All right, so let's do the next one. So, go quicker now. Probability of x is greater than or equal to 55. Well, what is 55? Because remember, this is probability of y is bigger than or equal to 55 now. Yeah? But we don't even have bigger than or equal to, because, well, yeah, let's do it. But remember, in a normal distribution, it's bigger than 55, but 55 doesn't exist. So this is why we need to backtrack here and go, oh, no, we need to do our continuity correction. So little diagram, 55. 55 is actually 55.5 and 54.5. So if we are saying bigger than or equal to, then it's got to include the whole number 55, doesn't it? Because it's at least. So this is bigger than, because normal distribution, there is no equal to, remember? This must be bigger than 54.5 because it includes the whole of it. And then we go to our normal distribution stuff. So 0.5, there's our 54.5. So it's everything here that we're looking for, which is the same as 1 minus probability of y less than 54.5. And then you do it as normal, okay? So I don't need to do that with you. Let's do just a bit more of that. Let's just practice then. So this is the same as probability of y. It's got to be less than, right? Because we don't work with less than or equal to in normal distribution. So the number 20 is actually 19.5 and 20.5. We're saying less than or equal to 20. So it includes the whole number of 20, right? And it's going towards the left. So actually this must be 20.5 because the whole of 20 is being included in that. And again, you do your normal stuff, you find out where that is, it's blah, 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 calculator. Okay? Probability of less than 125. So again, little thing, 125, but 125 is actually 124.5 and 125.5. So if I want to have less than 125, it does not include the number. So this is, really I should do approximate here. Less than, well, 125 is not included. So I take the lowest possible bound of what 125 is, and I'm here. Okay? And I would solve that as normal. So one final thing then. What happens if the question says, find the probability of x equaling 20? Well, we already discussed this. This is the same as the probability of y between 20.5 and 19.5. Because remember, y equals 20 doesn't exist in a normal distribution because it would be 0. The probability would be a 0. But 20 is no longer just 20. 20 is all this space. So if you want to find it, you need to go between 20.5 and 19.5. And you would solve that as normal. And that's the end of that.